Okay, let's unpack this. If you are building modern iOS applications, you know the truth. The app is only as good as its connection to the outside world. Networking is the critical circulatory system of your application. It's where the data flows, where the magic happens, and unfortunately, it's often where the most stubborn, low-level bugs hide.
Yeah, absolutely. It can get complex down there.
Our mission today is a deep dive into the modern iOS networking landscape.
Right.
We're decoding everything from the bedrock framework URLSession to the cutting-edge asynchronous APIs and the high-level architectural layers like Combine, Moya, and REST that keep complex apps stable and scalable.
Exactly.
If you want a comprehensive shortcut to truly mastering this entire stack, this is it.
And this mastery is, well, it's pretty much non-negotiable for professional development these days. It's no longer sufficient just to know how to, fire off a network request.
Right.
The standard now demands understanding why you chose a download task over a data task, how to manage concurrent operations without deadlocking the UI, and why certain APIs were designed to replace the older solutions. It's about the whole picture. Our source material offers a brilliant systematic roadmap for this. We'll move from the foundational Apple APIs up through the crucial process of data serialization, all the way to advanced architectural patterns. Think of it as the standardized, versatile wrapper around the lower level socket connections. It manages things like standard requests, getD, post, file uploads, downloads, while offering built-in support for authentication, caching, and credential storage.
Right.
Crucially, when we describe it as modern, we really mean it's inherently asynchronous. It offloads the work from the main thread immediately, which is just essential for mobile apps. You can't block that UI thread.
That brings us to the predecessor, NSURL connection, which Apple deprecated starting with iOS 9. For developers who started after, say, 2015, they might never have had to face the terror of the old way. What exactly made the old guard so obsolete, particularly regarding concurrency?
Oh, the differences were profound, yeah. And they directly relate to the shift in how we build apps today. NSURL connection operated with an older, much more challenging API style. It was often synchronous.
Synchronous. Ouch.
Exactly. Meaning, if you didn't manually shunt it onto a background thread using something like dispatch-queue.global.async, it would literally freeze the UI while waiting for the network response.
That's the dreaded frozen scrolling, the unresponsive button click, the sure sign of a terrible user experience. Nobody wants that.
Nobody. URLSession, however, was designed from the ground up to be asynchronous. It utilizes Grand Central Dispatch, GCD, automatically to manage these network tasks on concurrent queues.
So GCD is baked in.
Pretty much baked in, yeah. You tell URLSession what you want, and it handles the thread management and calls you back when the data is ready or if there's an error. That automatic integration with GCD is kind of the invisible foundation that keeps the UI smooth.
That makes sense.
And beyond concurrency, the API style just improved dramatically. NSURL connection was heavily reliant on delegate methods for every little piece of information data, arrival, error, completion. It got messy fast.
The delegate pattern can be quite verbose.
Very verbose. URLSession introduced clean, modern completion handlers and more recently native async await support in Swift, which really cleans up that pyramid of doom we used to see with nested callbacks. Much more readable.
Okay, that's a big win for readability and maintenance. And what about the practical use cases that drove the deprecation? The difference in how the frameworks handled background operations was a major deal breaker, right?
That was probably the biggest functional leap, yeah. If your app was backgrounded or suspended by the system, NSURL connection tests just stopped. They didn't persist. Poof, gone.
Not great for downloading a big file.
It's not great at all. URLSession, through its background configuration, allows the operating system to actually take over and manage tasks like large file downloads or uploads, even if the app itself is terminated by the system for memory pressure or whatever.
So the download continues.
The download continues. This made URLSession vital for any robust application needing to handle serious media content, large updates, that sort of thing.
Okay, so URLSession brought better efficiency, cleaner APIs, background support, and resource reusability. Let's dissect the four main components of its architecture now. We need to understand the relationship between the manager, the configuration, the unit of work, and the handler.
Sounds good. First, the URLSession itself. This is the container, the manager, you could say the central nervous system. You instantiate it, and it coordinates everything.
Like the traffic controller?
Yeah, exactly. Managing shared resources like the cache and cookie storage, and coordinating the life cycles of all the tasks associated with it.
Okay, so the coordination manager needs a rule book, right?
That's the second component. The URL session configuration. This is the rulebook. It defines the session's behavior. It dictates things like timeouts, cache policies, connection settings, whether to allow cellular access, things like that.
And our sources highlight 3 crucial types here.
Yes, and developers really need to choose wisely based on what they're trying to do.
Okay.
First, we have the standard all-purpose .default configuration. This is what you'll use probably 90% of the time. It supports persistent disk-based caching, cookies, and credentials. It's reliable, standard behavior.
Not a fumble.
Then there's the ephemeral configuration. Think of this as like the incognito mode for your network session.
Like in a browser.
Exactly like that. All data, caches, cookies, credentials, everything is stored only in memory, RAM. When the session ends or the app is terminated, that data is completely gone. No trace left on disk.
So good for sensitive data.
Perfect for sensitive transactional data or when you explicitly want to ensure no trace of the request is left on the device's storage.
And finally, the specialized configuration for persistence outside the app lifecycle, the background one.
Right. The third is background identifier. This configuration tells the system that the tasks initiated here should be managed by the OS itself and allowed to continue running even if your app process is terminated or suspended.
That's the magic for big downloads.
That's the magic. It's the only way to reliably handle long-running uploads or downloads. And that unique identifier is key. It allows the system to reconnect your app to the task results when the app eventually relaunches.
Okay, that makes sense. And the third component is the actual execution unit.
Yep, the URL session task. This represents a single unit of work, a single request, whether it's downloading a huge file or just fetching a tiny bit of JSON. It has a life cycle. It goes from suspended to running to completed or canceled.
One task per request.
One task per request. And finally, component 4 is the URL session delegate. Now, this is often optional these days thanks to completion handlers and async await.
Right, you don't always need it.
You don't always need it for simple cases. But the delegate is crucial for advanced use cases. It allows your app to handle events beyond simple success or failure. Things like handling authentication challenges, tracking granular download or upload progress, or responding to HTTP redirects, especially when background transfers are involved.
So for the complex stuff, the delegate is still your friend.
Definitely. For fine-grained control, the delegate protocols are indispensable.
Okay, let's focus on the task types then, because this is where developers often fall into memory traps, isn't it? If the listener only takes one thing away from this section, it should probably be the difference between memory and disk storage when choosing a task.
Absolutely, 100%. Misidentifying the appropriate task can lead to immediate crashes, specifically those nasty out-of-memory or errors.
Right. Nobody wants ohms.
So the data task, URL session data task, this is meant for short requests. Fetching JSON, small pieces of text, maybe small images or icons. The key characteristic is that the entire response data is accumulated and held entirely in memory, RAM.
All in RAM.
All in RAM. It's perfect for fast API calls, getting configuration data, that sort of thing. But using it for anything larger than, say, a few megabytes is an active risk. It consumes precious RAM that the system needs for everything else your app and other apps are doing.
And the risk escalates if the user has multiple data tasks running concurrently, especially on older or lower memory devices.
Yeah.
You're just asking for a crash then.
Precisely. Which is exactly why the download task, URL session download task, exists. This is your workhorse for large files, videos, PDFs, high-resolution images, archives, you name it. Instead of accumulating the data in memory, the operating system manages the download process itself, streaming the data directly to a temporary file on the device's disk storage.
Straight to disk.
Straight to disk. This completely bypasses the RAM limitation and is basically mandatory for file sizes that could potentially exceed your app's memory budget, which can be surprisingly small sometimes.
So data task equals RAM, download task equals disk. That distinction is absolutely crucial.
Got it. And the third type handles sending large data back to the server.
Exactly. The upload task, URL session upload task, is for transmitting data to the server. You have some flexibility here. You can upload raw data stored in memory if it's small enough.
Like posting a short JSON payload.
Right. Or if the data is massive, like uploading a video the user just recorded, you can upload it directly from a file that's already saved on the disk. Much more memory efficient.
And it supports backgrounding too.
Yes. This task also fully supports the background configuration we talked about, allowing for reliable large-scale uploads even if the user minimizes the app or switches to another one. Okay. And there was a fourth one. Less common.
Yeah, the fourth task, the stream task, URLSession stream task, is a bit of an outlier. It's used less often in typical app development. It's designed for custom network protocols or for continuous data flows, like setting up a WebSocket connection. It basically provides a persistent, low-level TCP/IP connection that allows for bidirectional communication streams.
Gotcha. More specialized use cases. Now back to the delegates for a moment. We mentioned they handle advanced events. Why would a developer use the specialized URLSession day delegate instead of just simple completion handler for a data task, assuming the data isn't huge?
Well, even if the total data isn't astronomically huge, maybe it's large enough to cause a noticeable memory spike if it all arrives at once. A standard completion handler only delivers the entire response data once the request is fully finished.
Okay.
But maybe you have, say, a 50 millibit JSON payload. It might fit in memory, but it's still a big chunk. The URLSession data delegate is used to handle that data incrementally. It has methods that get called repeatedly, receiving data in smaller chunks as it arrives from the network.
So you can process it piece by piece.
Exactly. This is essential if you need to perform processing on the data before the entire response is finished downloading. Or maybe you want to mitigate that memory spike by immediately parsing and storing chunks in a database, or writing them to a file on disk as they come in. It makes the data task more memory-friendly for larger payloads.
That's clever. And for the download task, the delegate specializes in handling the file once it's on disk.
Right. The URLSession download delegate is vital because it manages the transition from the temporary download state to a permanent state. The system downloads the file into a temporary system-managed location on disk. The delegate's completion method, URLSession.downloadTask.didFinishDownloading2, provides you with the URL of that temporary file. And it is your responsibility, right there within that method, to move or copy that file to a permanent, safe location in your app sandbox before the method returns. If you don't, the system cleans up the temp file and your download is lost.
Critical step then. Move the file.
Absolutely critical. It's also where you get callbacks for tracking granular download progress, like updating a progress bar and managing the resumption of interrupted downloads.
Makes sense. Let's move to session management itself. We have the super simple URLSession.shared instance and the more involved custom session setup. When should a developer, particularly maybe a learner or someone prototyping, resist the tempting simplicity of the shared instance?
The shared session, URLSession.shared, is definitely tempting because it requires zero configuration. It's a convenient singleton managed by the system, ready to go, but that convenience comes at a pretty severe cost. It's very restrictive.
How so?
It uses default configurations only. That means you cannot set custom cache policies globally. You can't define custom HTTP headers that apply to all requests made through it. You can't restrict it to Wi-Fi only. And most critically, it does not support background transfers or custom delegates. It is strictly completion handler or async await only.
So if I just need to hit a quick public API to pull down today's weather forecast, maybe shared is fine.
Yes, exactly. For quick prototyping or simple single-use, non-critical API calls where you don't need fine-grained control, it works great. Fetching a small JSON payload once, maybe?
But anything serious needs a custom setup.
Pretty much any professional-grade application that requires finer control, like setting authentication headers across all requests consistently, or maybe throttling requests when the user is on cellular, or defining specific network timeouts, or implementing any kind of background transfer, must use a custom session. There's no way around it.
Okay.
A custom session is created by initializing URLSession with a URLSession configuration object that you define. You get full control over the session's lifespan, the caching behavior, the network protocols used, cookie handling, and importantly, you can assign those custom delegates we talked about for progress tracking or background events.
So you trade maybe 5 extra lines of setup code for complete control.
Exactly. Complete control over resource utilization, reliability, and behavior. Usually a worthwhile trade-off for anything beyond trivial tasks.
All right, now we shift gears a bit. We've covered the plumbing of how iOS talks to the network. Let's talk about the language of what it's typically saying. The dominant pattern for web APIs is REST. For those who might be newer to this concept, what are the fundamental building blocks of representational state transfer.
Right, REST. It's important to remember REST is an architectural style, not a specific protocol like HTTP itself. It was defined by Roy Fielding in his dissertation, and it dictates a set of constraints for how networked systems should communicate to be scalable and maintainable.
Okay, an architectural style, what are the key constraints?
The first big one is client-server separation. The client, our iOS app, and the server, the backend API, should be completely separate concerns. They evolve independently. The client knows nothing about the server's internal storage or business logic, and the server knows nothing about the client's UI state beyond the current request.
Decoupling.
Total decoupling. This is what makes rapid parallel development possible, with different teams working on the front end and back end. Second, statelessness. This is fundamental to REST. The server cannot or should not rely on remembering anything about the client from previous requests.
So each request is self-contained.
Exactly. Every single request from the client must contain all the information necessary for the server to understand and process it. This often means including authentication tokens, specific identifiers, or the full request body each time. It makes the system more resilient. If a server instance crashes, the client's next request can just go to another instance without losing context.
And the core concept of organizing the whole system around resources.
That's the third key point. Everything in the system is modeled as a resource, a user, a product, an order, whatever. Each resource can be uniquely addressed by a URI, which we usually call an endpoint. Think of the resource as the noun in the conversation. And the action we want to take on that resource is the verb, which is supplied by the standard HTTP methods. Finally, a core principle is that responses should be cacheable whenever possible to improve performance and save bandwidth on repeated requests for the same resource.
Let's detail that relationship between the action, the verb, and the HTTP method. This often maps to CRUD operations, right? Create, read, update, delete.
It's a very clean mapping, usually. If you want to retrieve data, read, you use the GET method, like get users123 to fetch user123's profile.
Makes sense.
If you want to create a new resource, say registering a new user or posting a new message, you use post, typically submitting the resource's data, like user details, in a JSON body to a collection endpoint, like POST users.
Okay. POST for create.
If you want to update an existing resource completely, replacing the entire thing with new data, you use POTT. For example, POT users123 with a full JSON body representing the updated user profile.
Replacing the whole thing.
Replacing the whole thing. And we absolutely must highlight the distinction between POT and patch. Patch is used for partial updates.
Just changing one field.
Exactly. If you only want to change a user's email address or update their profile picture without touching their name or bio, patch is the more efficient and semantically correct choice. You send only the fields you want to change, like patch users123 with just email, new.email at example.com.
Got it. Put replaces. Patch modifies.
Precisely. And finally, delete does what it says on the tin. It removes the resource. Delete users123 would delete that user. Mastery of these verbs and when to use them is key to a good RESTful client implementation.
Okay, that covers standard REST. Now we introduce the concept that often separates academic REST theory from real-world implementation. HTOS. Hypermedia as the engine of application state. Sounds complex, but also kind of perfect.
Yeah.
What exactly is HTOS demanding from the API?
HTOS, it's one of the original constraints of REST that's often, let's say, conveniently ignored in practice. It demands that the server doesn't just return static data in its responses, but also returns hypermedia links and possible actions the client can take next based on the current state.
Links, like HTML links.
Conceptually similar, yes. Imagine requesting a user profile. A HTOS compliant response wouldn't just give you the user's name and age. It would also include links embedded in the JSON, maybe something like links self2af, a piv1 users 123 update profile, href, a piv1's users 123 update fetch friends, ref, a pv users 123 friends outlets on.
So the response tells the app what URLs it can hit next. The application state is driven by the links the server provides, not by hard-coded URLs built into the iOS app itself. How does this provide, dynamic navigation?
It creates a highly decoupled system, which is the main goal. If the backend team decides to reorganize their API URLs, say changing V1 users to V2 accounts, a strictly HUS-driven client code shouldn't break.
Why not?
Because the client never relied on V1's users being a fixed hard-coded string in its code. It just relies on finding the link with the relation tag, the rel of update profile in the response it receives, and then using the href provided in that response for the next request.
So the client adapts automatically if the URLs change on the backend.
That's the ideal, yes. It also dramatically reduces the need for client updates. If the server adds a new capability, like a send message action for a user profile, it just adds a new link to the response JSON. An iOS app built to parse and display available links could potentially show that new send message button without needing a full App Store submission and update. The app becomes more discoverable and adaptable.
Okay, this sounds genuinely amazing for long-term maintainability. Yet, our sources emphasize that most iOS apps, and frankly most APIs, ignore HUS.
Why? What's the concrete complexity trade-off that makes teams skip it?
It really is a clash between architectural elegance and, well, developer pragmatism and deadlines. While HUS is arguably ideal for long-term maintainability and future-proofing, it introduces immediate non-trivial complexity on the client side during initial development.
How so?
Well, think about parsing. When you receive fixed JSON structure from a documented endpoint, you can use Swift's wonderful codable protocol to directly map that JSON into neat type-safe Swift structs or classes. It's clean, easy, and compile time checked.
Codable is great. It is. But when you receive dynamic hypermedia with embedded links, your client code has to do more work and needs to. A, parse a potentially generic links collection structure within the JSON. B, dynamically look up the specific links it needs based on those rel tags, like finding the update profile link. And C, build the subsequent network request using that dynamic URL it just extracted.
So you lose the direct type-safe mapping.
You lose that tight, predictable, compile time checked relationship between a fixed endpoint URL and a specific codable model structure. You're dealing with more string lookups and potentially more optional handling at runtime. It adds a layer of indirection and parsing logic.
So developers often prefer the perceived safety and simplicity of fixed documented endpoints, where they know exactly what the URL is and what the model structure will be, even if it means the app might break and need redeploying if the backend URL changes.
Exactly that. The initial development costs, the added testing complexity, and the ongoing cognitive load of dynamic link parsing often seem to outweigh the theoretical benefit of long-term decoupling for many fast-paced mobile development teams. The predictability and simplicity of fixed API contracts usually win out in practice. Pragmatism over purity, you could say.
Okay, let's transition smoothly from defining the conversation to actually consuming it. Data serialization, particularly parsing JSON, was, let's just say it was painful before Swift 4. We really need to illustrate why the arrival of the codable protocol felt so revolutionary for iOS devs.
Oh, absolutely. Revolutionary is the right word. Before codable, the standard approach relied on NSJSON serialization. This is a lower-level API, and it would basically convert the raw JSON data object into foundation objects, typically dictionaries, NS dictionary, or string, any, and arrays, and array, or any.
Okay, so you get dictionaries and arrays. What was the nightmare part?
The nightmare was the next step, getting your actual type data out of those dictionaries and arrays. You would have to manually access values using string keys like JSON dictionary username. Then, critically, you had to force cast or conditionally cast as those any values to their expected Swift types, like string or int or double.
Lots of iflet or guardlet statements.
So many guardlet statements. It looks something like guardlet username, old JSON dictionary username as string else. Throw my custom parse error dot missing username. This code was incredibly verbose, required exhaustive manual error handling for every single field. What if the key is missing, misspelled, wrong type? And most importantly, it was entirely untype safe at compile time.
Meaning, if the backend changed a key name from username to username, your app wouldn't know until it crashed in production.
Precisely. The compiler couldn't help you. It was a recipe for runtime failures just waiting to happen, triggered by silent backend changes. It was brittle.
Enter codable.
Enter codable. This is actually a type alias in Swift that combines two protocols. The encodable protocol for turning your Swift objects into data, like JSON, and the decodable protocol for turning data, like JSON, into your Swift objects.
So it handles both directions.
Both directions.
Yeah.
By simply declaring a Swift struct or class as conforming to codable, example, struct user, codable, you delegate the entire tedious, error-prone parsing process to Swift's standard library, specifically essentially the JSON decoder class.
And the benefits.
It is type safe. The compiler checks that your struct properties match what can be decoded. It's incredibly concise, often requiring zero extra code if your property names match the JSON keys. And it requires virtually zero boilerplate parsing logic for standard structures. The compiler validates the structure for you before you even run the app. Huge win.
But the real world is often messy, as we know. Backends frequently use snake case for keys, like first name, while Swift convention strongly prefers camel case, like first name. We can't just force the entire backend team to rename all their keys to match Swift style. How does Codable handle this super common issue of mismatched naming conventions?
Yeah, that's a classic problem, and Codable has an elegant built-in solution. Coding keys.
Coding keys, okay.
When the default automatic mapping fails because the property names in your Swift struct don't exactly match the keys in the JSON, you define a special nested enum called coding keys inside your Codable struct.
An enum inside the struct.
Yep. This enum must conform to two protocols: string, for the raw JSON key value, and coding key, the marker protocol. Inside this enum, you define a case for every property in your struct. If a switched property name matches the JSON key, you just list the case name, purgy case aid. But for every property where the JSON key doesn't match the Swift property name, you define the case using the Swift name, and you explicitly assign it the JSON key string as its raw value. For example, case first name. Or maybe paste profile URL equals profile image role.
So you create a specific map right there.
Exactly. It's a declarative mapping. The JSON decoder automatically recognizes this coding keys enum if it exists and uses it to translate between the JSON keys and your Swift property names during decoding, and encoding too if you use JSON encoder.
This is a perfect example of a feature that, post Swift 4 has just drastically improved the developer experience. It completely eliminates what used to be a massive amount of manual effort, often involving custom initializers from decoder, encoder, and complex mapping functions, and centralizes it all into one clean, readable, declarative enum.
It really does. And it also means that if the backend did unfortunately change a key name later, you likely only have one central place that coding keys enum to update in your model layer, not potentially dozens of scattered string literals in custom parsing logic. Much more maintainable.
Makes sense. We mentioned NS-JSON serialization earlier, the old way. Is there any reason a developer might still reach for that lower-level API today, now that we have Codable?
It's much rarer now, but its primary remaining use case is handling highly dynamic or truly unknown JSON structures. Imagine an API where a results field could contain an array of user objects one day and an array of completely different post objects the next, and you need to somehow inspect the raw structure before you even attempt to decode it into a specific codable type.
So when you don't know the shape beforehand.
Right. In those cases, you might first use NS-JSON serialization to convert the raw data into a loosely typed string, any dictionary or any array. Then you could inspect keys or types within that dictionary array to figure out which specific codable type you should then try to decode it into using JSON decoder. But this is definitely an edge case.
So the recommended path is definitely Codable and JSON decoder.
Absolutely. JSON decoder is the highest level, most reliable, and type-safe tool for, I'd say, 99% of JSON parsing tasks in modern Swift. It integrates seamlessly with the Codable protocol and Swift's type system.
And we should probably offer a brief moment of silence or acknowledgement for the third-party libraries like SwiftUI or Object Mapper. They were absolute lifesavers before Codable arrived on the scene.
Oh, they absolutely were. They filled a critical gap. They cleverly solved the complexity and safety issues of NS-JSON serialization using custom operators, safer unwrapping patterns, and object mapping features. Huge credit to them.
Yeah.
But the fact that Apple eventually embraced this problem and delivered a standardized built-in solution with Codable meant that developers could finally shed that extra dependency. This leads to potentially faster build times, smaller app bundles, and crucially, a more standardized, universally understood approach to data handling across the ecosystem. Codable just became the default way.
Okay, moving now into what feels like the truly modern toolkit, especially since iOS 13 introduced Combine. This is Apple's framework for reactive programming, and for many developers, it represented a pretty massive shift in mindset compared to traditional callbacks.
Yeah.
How does Combine fundamentally change how we approach asynchronous operations like networking?
Combine is a big deal, yeah. It formalizes the process of handling asynchronous data streams and events over time using a declarative model. Instead of writing nested callbacks, defining sequential steps, do this, then if success, do that, else handle error, you define how data should flow and what transformations should happen to it along the way.
A declarative pipeline for data.
Exactly, a pipeline. The three key players, the core concepts, are critical to wrap your head around. First, you have the publisher. This is the source of truth, the thing that emits a sequence of values over time. It could emit 0 values, 1 value, many values, and eventually it either completes successfully or fails with an error.
And URLSession has publishers.
It does. URLSession integrates beautifully here with methods like URLSession.shared.data_task_publisher for .url. This specific publisher emits a tuple containing the raw response data and the URL response exactly once, then completes or errors out.
Okay, so the publisher does the work and emits the result. What consumes it?
Right. That's the subscriber. This is the entity that listens to or subscribes to a publisher. It's the endpoint of the pipeline. It defines how to handle the incoming values using its receive value method and how to handle the terminal state, completion or failure, using its receive completion method.
And nothing happens until you subscribe.
Critically, yes. Publishers are often lazy. Nothing actually happens. No network request is made, no data flows until a subscriber actively attaches to the publisher. That act of attaching is called the subscription.
Okay, publisher and it's a subscriber receives. What about the middle?
Ah, the magic in the middle. That's where the powerful operators come in. These are essentially functions that take a publisher as input, transform the data stream in some way, and return a new publisher as output. You chain these operators together.
Like map and filter.
Exactly like map and filter from sequence processing, but for asynchronous streams. For networking, common operators include try_map to extract just the data from the publisher's tuple and potentially throw an error, decode, which automatically runs a JSON decoder with your codable type for you, map to transform the decoded object, filter to ignore certain results, catch to gracefully handle errors and perhaps return a default value, receive to ensure the final result is delivered back to the main thread for UI updates. There are dozens.
You build a chain. Publisher, operator, operator to subscriber.
Precisely. A clear, readable, declarative pipeline describing the entire asynchronous workflow.
The real power here, especially for networking, seems twofold. One is just reducing the nested boilerplate code, the pyramid of doom.
Definitely cleans that up.
And the other seems to be about automatic handling of resource cleanup, like canceling requests.
Yes. The cleanup or automatic cancellation is a huge benefit. In traditional URLSession with completion handlers, if a user navigates away from a screen while a request is in flight, you must remember to manually find the URLSession task object and call.cancel on it to prevent wasting resources and potential memory leaks or unexpected callbacks later.
Easy to forget.
Very easy to forget, especially in complex views. In Combine, when you subscribe, usually using .sync or .assign, the subscription process returns an any cancelable object. You typically store this cancelable in a set associated with your view model or view controller. When that view model or controller is deallocated, Radaji, the screen is dismissed, the any cancelable objects it holds are automatically deallocated too, and this triggers the cancellation of the entire Combine pipeline, including the underlying network task.
So cleanup happens automatically when the owner disappears.
Exactly. It prevents dangling network requests and significantly reduces the mental load on the developer regarding manual cancellation logic. It's much safer by default.
Okay, Combine is powerful. Let's pivot slightly to popular external libraries. AlamoFire has been, for many years, arguably the standard third-party networking library in the Swift world. Given how much stronger Apple's native tools are now, especially with Combine and native async for URLSession, is AlamoFire still necessary? Or is it maybe just syntactic sugar at this point?
That's a really fair challenge, and the answer is, well, it's nuanced. AlamoFire is indeed a high-level wrapper built directly on top of URLSession. And yes, Swift's native capabilities have caught up significantly. However, AlamoFire still offers some significant quality-of-life improvements and robustness features that arguably go beyond mere syntactic sugar for many teams.
Like what specifically?
Its primary advantages often lie in centralized request management and a suite of robust, battle-tested built-in features. It generally provides a cleaner, more fluent API for creating requests, especially when you're dealing with more complex scenarios like multi-part form data uploads for images files, managing custom headers consistently, or intricate parameter encoding.
Okay, easier setup for complex requests.
Right. It also standardizes error handling into a specific AFAIR enum type, which can make downstream error processing and interpretation much cleaner than trying to parse the various underlying URL layer codes and domains yourself.
Standardized errors. Nice.
And perhaps most importantly for many, it offers highly developed chainable features like automatic request validation, for example, easily ensuring the HTTP status code is within the success range, say 200 to 299, before even attempting to parse the response. And it provides robust, simplified response serialization directly into your codable models, often with less code than the raw URLSession equivalent, especially when combining validation and decoding.
You mentioned response handling.
Yeah.
Walk us through AlamoFire's response mechanism, because that standardization seems to be its real secret sauce.
Yeah.
How does it process a response?
Yeah, it has a pretty precise chained workflow when a request completes. First, if you've added any, it performs chain validation. This is where it checks things like the HTTP status code or the response content type header. If any validation fails, it immediately errors out with a specific AFAIR.
Okay, validation first.
If validation passes, or if none was configured, it moves to the response serializers. These are specialized components responsible for converting the raw response data into something more useful. AlamoFire provides built-in serializers for common types like string, raw data, JSON, as any, and most importantly, a generic decodable serializer that works directly with your codable types.
So it handles the decoding automatically if you tell it to type.
Exactly. You just say response decodable of .user.self, and it handles the JSON decoder part internally. Finally, it bundles the result, either the successfully decoded value, like your user object, or a detailed AFAIR if anything went wrong at any stage, into a clean response object, like AF data response user. This consistent generic structure makes it really easy to handle results and integrate AlamoFire into different app architectures.
That does sound quite streamlined. Now let's go one level higher in abstraction. Moya. If AlamoFire is a helpful wrapper around the URLSession tasks, Moya positions itself as more of a network abstraction layer. What specific problem is Moya designed to solve that AlamoFire or raw URLSession might not?
Moya aims squarely at solving the problem of scattered network code and lack of type safety at the API definition level. If you use bare URLSession or even just AlamoFire directly in your view models or service classes, you often end up defining API endpoints, constructing URLs, setting headers, and encoding parameters repeatedly, maybe slightly differently, all over your code base.
Yeah, that sounds messy and hard to test.
It becomes a real mess, exactly. Hard to test, hard to mock, hard to maintain, hard to ensure consistency. Moya enforces structure by requiring developers to define all API interactions through a single unified type-safe Swift enum that conforms to Moya's core protocol, target type.
The target type protocol. Okay, that sounds like the spine of the Moya layer.
Yeah.
What specific properties does this protocol require the developer to define for every single API call they want to make?
Right, the target type is central. When you create your API enum, say on a My Network API, and make it conform to target type, you must implement several properties for each case in your enum, where each case represents a specific API endpoint, like .getUserProfile, user_string, or .updateUserProfile. You have to define one .base URL, the base URL for the API, often the same for all cases, two path, the specific path component for this endpoint, e.g. the 3 method, the HTTP method, like .get, .post, .patch, for .task. This is a crucial one. It defines the request parameters and how they're encoded. Options include request plane, no parameters, request parameters.encoding for URL query or HTTP body parameters, .upload multipart nilin, download destination, etc. 5 headers. Any specific HTTP headers required for this endpoint, like content type or custom headers.
So everything needed for that specific API call is defined right there in the enum cases implementation of those properties.
Exactly. It centralizes the entire definition of your API surface in one place. This makes the network layer incredibly predictable, easily mockable for unit tests. Moya has great testing support, and much easier to maintain because if an endpoint changes, you know exactly where to update it.
That's very structured. And Moya introduces another brilliant concept called plugins to handle things that cut across multiple API calls, like logging or authentication. Explain what plugins are and how they save developers from writing tons of repetitive code.
Plugins are one of Moya's most elegant features. Think of them as interceptors or middleware. They allow you to hook into the lifecycle of a network request just before it's sent or just after a response is received and observe, modify, or add behavior automatically without having to clutter the core target type definitions for each endpoint.
So they apply globally, or at least to the Moya provider instance.
Exactly. You typically create a Moya provider instance, which is what you use to actually make requests, and you pass an array of plugins to its initializer. Those plugins will then be applied to every request made through that provider.
What's a classic example? Authentication.
Authentication is the perfect example. The access token plugin is commonly used. If your API requires a unique authorization header, like a bearer token, to be sent with most or all requests, instead of manually adding that header logic inside the headers property for every single enum case in your target type.
Which would be tedious and error-prone.
Totally tedious. Instead, you just configure an access token plugin with logic to retrieve the current token, and you add that plugin to your Moya provider. The plugin then automatically intercepts every request just before it's sent, injects the necessary authorization header with the current token, and then lets the request proceed. Sensitive authentication logic is centralized in one place.
That's incredibly useful. What are some other common built-in or custom plugins people use?
The Network Logger plugin is indispensable during development. It automatically prints detailed information about the request, URL, method, headers, body, and the response, status code, headers, data, directly to the console. Super helpful for debugging. The Network Activity plugin is great for UI feedback. It monitors when network requests start and finish, and it can trigger callbacks that you use to show or hide a global loading indicator, maybe the little network activity spinner in the device's status bar.
The spinner.
That's the one. And Moya makes it easy to write your own custom plugins, too. People write plugins for things like custom error handling and mapping, automatic request, retrying logic based on certain conditions, response, data caching, and more. Plugins provide a really clean way to add cross-cutting concerns to your networking layer.
Okay, let's shift focus now to optimization and reliability. A fast app often feels like a more reliable app, and caching is absolutely core to achieving that speed. It reduces latency for the user, it saves their data usage, which they appreciate, and it's essential if you want any kind of decent offline capabilities. What are the main caching strategies an iOS developer needs to have in their toolkit?
Yeah. Caching is crucial. We can generally categorize the main approaches based on where the data is stored and how long it persists. There are about 5 key strategies.
5.
First, there's URL cache, which we touched on briefly with URLSession. This is the built-in HTTP caching layer that's managed automatically by URLSession itself. It operates based entirely on standard HTTP cache control headers sent by the server, like cache control expires, etag, last modified.
So it's automatic, but depends on the server playing nicely.
Exactly. It's simple to use because it's often on by default. Default configuration uses it. But your control is limited to interpreting and respecting what the server's headers dictate. You can configure its size, memory, and disk capacity, but not usually the specific caching logic per request beyond the standard policies.
Okay. Built-in HTTP caching. What's next?
Second, in-memory cache. This is where you manually store fully parsed Swift objects or maybe UI image objects directly in RAM. The standard class for this in iOS is NSCache.
NSCache, right. Like a dictionary, but memory-aware.
Precisely. It behaves like a dictionary, key value storage, but it's specifically designed to automatically evict objects when the system is running low on memory, helping prevent your app from being terminated. Access is incredibly fast, nearly instantaneous, since it's just pulling from RAM.
But it's volatile.
Highly volatile. When the app terminates, or if it receives a memory warning from the system, the cache can be partially or fully cleared. So it's ideal for storing temporary, frequently accessed data that's maybe expensive to compute or fetch, but not catastrophic if it disappears. Things like recently viewed user avatars, decoded JSON models for the current screen, maybe temporary UI elements.
Okay, fast but temporary. If we need the data to survive an app restart, we absolutely must move to disk storage.
That's strategy number 3. On-disk cache. This involves persistent storage, usually leveraging the device's file system directly, saving data to files in the app's caches or application support directory, or using a dedicated local database like Core Data, Realm, or SQLite.
Slower access than RAM.
Definitely slower to read from and write to compared to RAM, but the huge advantage is persistence. The data survives across app launches and even potentially across device restarts, depending on the exact location and system cleanup policies. This is mandatory for large assets that you can't keep in memory. Downloaded documents, large videos, offline map tiles, vast collections of images, etc.
Makes sense. Strategy 4.
Strategy number 4, which is very common, especially for things like image loading libraries, is the hybrid cache. This smartly combines the speed of an in-memory cache with the persistence of an on-disk cache.
Best of both worlds.
Kind of, yeah. The typical logic is, when data is requested, first check the fast in-memory cache. If it's found, a cache hit, return it immediately. If not, a cache miss, then check the slower on-disk cache. If found there, load it from disk, return it, and also potentially copy it into the in-memory cache for faster access next time.
And if it's not on disk either.
Only then, if both caches miss, do you fall back to actually fetching the data from the network. This layered approach provides a great balance of speed for recently accessed items and resilience for items accessed less recently or after an app restart.
Okay, hybrid. And the final, most flexible approach.
The fifth strategy is what we might call manual custom caching, often involving a database. This is when a developer explicitly writes application-specific logic to store, manage, and retrieve API response payloads, like parsed JSON objects, within a persistent local database, like core data or realm.
So you're not just caching raw data, but structured objects.
Exactly. This provides the maximum level of control over the data relationships, defining custom expiration logic, enabling complex querying of the cached data, e.g., find all cached articles matching these criteria, and managing data synchronization. It's typically used when the app needs extensive, queryable offline support, like building an offline-first newsreader, a complex dashboard that needs to work without connection, or managing large data sets locally.
Very powerful, but also the most complex to implement.
Definitely the most complex, requires careful data modeling and synchronization logic.
Let's zoom back in on the built-in system, URL cache. You mentioned it respects server headers. One of the most powerful aspects of it, from a network efficiency standpoint, is the bandwidth saving achieved through cache revalidation. Can you explain the process of that HTTP handshake using, say, an E tag, and what happens with that magical 304 not modified status code?
Yeah, this is a really beautiful example of how HTTP is designed for efficiency. When URLSession, using a configuration that enables URL cache, needs to make a request for a resource it has previously fetched and cached, it first checks the cache policy based on the cache control or expires headers from the original response.
Okay, checks if it's stale.
Right. Now, if the cached version exists but the headers indicate it might be stale, for example, its max age has passed, the session doesn't just immediately discard the cached data and fetch the entire resource again. That would be wasteful if the data hasn't actually changed on the server.
So what does it do instead?
Instead, it performs cache revalidation. It sends a conditional request back to the server for the same URL. This conditional request includes special headers derived from the cached response. Typically, it sends either the if-none-match header containing the e-tag value from the cached response, and e-tag is like a unique identifier or fingerprint of the resource content.
Right.
Or if an e-tag wasn't provided, it might send the if-modified-since header using the last modified date from the cached response.
Okay, sends a lightweight check.
A very lightweight check. The server receives this conditional request, it checks the provided e-tag against the current version of the resource it has, or compares the if-modified-since date. If the server determines that the resource the client already has, identified by the e-tag or date, is identical to the current version on the server, then the server responds with a tiny HTTP response header containing the special status code 304, not modified. And crucially, the server sends no response body data at all.
So the app gets a tiny, yep, you're still good signal, uses the version it already had stored locally in URL cache, and saves potentially megabytes of bandwidth by not re-downloading the same data.
That's the entire magic right there. The 304 response tells URLSession to go ahead and use the cached copy it already has, marking it as fresh again. It saves enormous amounts of data transmission time and cost for the user and reduces load on the server. It's a win-win.
And if the resource is changed on the server?
If the server detects the resource is changed, the e-tag doesn't match, or it's been modified since the date, then it ignores the conditional headers and just sends back the full new resource with a normal 200 OK status code and the new response body, which the client then uses and caches.
Brilliant. Okay, finally, reliability often requires knowing the current state of the network connection itself. You don't want to fire off requests if the user has no internet. How do modern iOS apps handle checking network reachability these days? What's the preferred way?
Yeah, knowing the network status is key. The older method, using SE network reachability from the low-level system configuration framework, still works, but it was often a bit clunky to use and primarily gave you a binary answer. It essentially told you, yes, there seems to be some kind of signal to the target host, or no, there is not. That's often insufficient for modern needs.
Not enough detail.
Not enough detail, exactly. The modern, strongly preferred approach available since iOS 12 is using NW Path Monitor, which is part of Apple's newer network framework, the network.framework.
NW Path Monitor, okay?
This API is much more powerful. It doesn't just check for connection once, it monitors the network path continuously. It provides updates about the current path status, including whether the path is currently satisfied, meaning it's usable for network traffic, what interface type is active, like Wi-Fi, cellular, wired Ethernet, or even others like loopback, and crucially, whether the current connection is considered expensive, like a metered cellular data plan, where the user might want to conserve data.
Knowing if it's Wi-Fi versus cellular, and if cellular is expensive, is really useful.
It's incredibly useful. This granularity allows for truly intelligent network behavior in your app. For instance, you might use NW Path Monitor to observe the path status. If the connection drops, you can pause outgoing requests and maybe show an offline UI. If the connection comes back but it's on an expensive cellular interface, you might decide to defer large background uploads or downloads until the monitor tells you the user has switched back to an inexpensive Wi-Fi interface.
So it enables smarter decisions based on the actual network conditions.
Exactly. It allows for much more context-aware and user-respecting network management compared to the old reachability checks. It's definitely the way to go for modern iOS development. #tag8 inclusion and final thought.
Wow, this has been an incredibly detailed journey through the core technologies, the architectural patterns, and the modern tooling surrounding iOS networking. To really synthesize this for the listener, if we had to boil it down, what are maybe the 3 most pivotal insights or takeaways we need to solidify from this deep dive?
Okay, 3 key takeaways. First, absolutely know your foundation and critically manage your memory. URLSession is the core engine. Your decision between using a data task, which loads everything into RAM, and a download task, which streams data to disk, is often the decision point that saves you from those dreaded midnight crash reports due to out-of-memory errors. You absolutely must respect the memory boundary.
Right. Memory first. What's second?
Second, fully embrace Swift's native solutions where they shine. The Codable protocol was truly a revolution, eliminating countless lines of fragile, error-prone manual JSON parsing code. Features like coding keys allow us to seamlessly bridge the gap between messy back-end naming conventions and clean, type-safe Swift architecture. Use the tools Apple provides.
Leverage Codable. Got it. And third?
Don't be afraid to use abstraction layers to manage complexity as your app grows. Whether you adopt the declarative power of combine chains for handling asynchronous events and cancellation cleanly, or you implement architectural frameworks like Moya to enforce structure, consistency, and testability via the target type protocol, moving beyond scattered, repetitive network code is paramount for building maintainable professional applications. Structure matters.
Structure matters. Yeah. And as you mentioned much earlier, all of this high-level asynchronous networking we've discussed, the URLSession tasks happily running in the background without freezing the app, is only possible because of Apple's underlying concurrency system, Grand Central Dispatch, GCD, working behind the scenes, right?
That's exactly right. GCD is really the invisible infrastructure making all this efficiency possible. When URLSession completes a network task on one of its background threads, it's GCD utilities, like dispatching the result handler back to the dispatch queue.main, the main UI thread, that allow the developer to safely update UI elements with the fetched data. It's the essential conductor orchestrating all this concurrent work, managing thread pools, and ensuring main thread safety, which ultimately prevents the UI from locking up while we're waiting for data from the internet. You don't always see it directly with URLSession, but it's always there.
The unsung hero.
Pretty much. Finally, let's maybe revisit that interesting tension we explored back in the rest section regarding HTOS. We established that while HTOS represents this elegant architectural ideal of a truly dynamic, hypermedia-driven, server-controlled client interface, its strict implementation remains pretty rare in the wild, largely due to the immediate coding complexity it introduces on the client side. Developers, for better or worse, often prefer the pragmatism of fixed, well-documented endpoints paired with simple, predictable, codable models.
Yeah, the pragmatic approach often wins.
It often does. So this raises an important, maybe provocative, forward-looking question for you, the listener, to consider. As development tools, particularly AI-powered code generation and analysis tools, become more sophisticated and adept at handling complex boilerplate code and dynamic parsing, Will the perceived cost of implementing a truly HadeOS compliant client eventually fall so low that the superior long-term architectural benefits, things like easier API evolution, dynamic feature discovery, the ability to deploy new server-driven flows without ever updating the client app, finally outweigh the current developer bias towards fixed, simple API contracts?
Will the tools make HadeOS finally practical for the mainstream?
Exactly. It's a question about whether the tooling can bridge that gap between architectural purity and development velocity. The relationship between client and server is constantly being redefined by the tools and frameworks we use, and this tension between static contracts and dynamic hypermedia remains a really key area to watch in the future of API design and consumption.